So I'm pleased to introduce Ian Convy, who's going to be talking about using some of these ideas, tensor networks and quantum computing in machine learning. So the title of his talk is Interrogating the Tensor Network Regression Model. I'm happy to welcome Ian from Berkeley. Thanks.
Thank you. My name is Ian. I'm going to be talking about interrogating these kind of models. So what that means, give a little overview. So I'm going to start by, just because in the spirit of this being quantum computing and this network talk, I'm going to start by introducing a very popular kind of quantum machine learning model called the variational quantum circuit. I'll describe that a bit, and then I'll sort of take a step back and show how that is just one kind of example of a broader class of models called tensor network regression models, and explain that in more general detail outside of the quantum context exclusively. And then after that, I will discuss two works that I've been a part of that have tried to probe how these kind of models work, and in particular, whether or not this sort of very large feature space they use is necessary, whether you can break it apart into small pieces and still get as good a performance as the full thing. That'll make more sense as we go on, but that's the idea. Talking about two papers, one that I did with a fellow graduate student in the Whaley group at Berkeley, Hao-Ran Lau, and then also have a paper that I did with my PI, Professor Whaley, at the end. Okay, so just to begin, set the stage, I'm focusing on machine learning, in particular, focusing on regression, to kind of supervise machine learning type. Basic idea, regression is a very broad term. The basic idea is that you have some set of variables called features, and some set of variables called labels. And the idea is that the features are generally easy to get, fairly easy to work with, and the labels are hard in some way. And the idea is you want to design some algorithm to take the features, which is the easy thing, and give you the labels for the hard thing. That's just the broad idea of regression. In particular, I'm focusing on what's called parametric regression, so parameterized regression. And the idea here is you have some function, so we'll say y vector here are a vector of labels, what I want to predict. X here is the features, what I'm going to use to predict. And then f is just some functional representation of my algorithm that I sort of tune, or its behavior is determined by some set of parameters theta, just general vector that holds all the parameters. Now, one example you've probably seen is linear regression. So you have your output y, just have some matrix w, acts on your vector of features, gives you an output. That's some of the most basic, but also probably the most common forms of parameterized regression. Now, the one that is probably the most well-known and famous is the neural network. Probably for its astounding success in doing a lot of hard problems. Well, just before I go to that, it's just an example of the kind of tasks that I'm focusing on here, and that's pretty representative of kind of tasks that you often want to do in machine learning. So image classification is a big one. I'm focusing on this. In this case, the features are pixels. So your X vector here is just a bunch of pixels. Your Y's are class probabilities in this case. So you have some set of classes. It could be digits. It could be articles of clothing. And you want to get an output that gives you probabilities that your image is one of those classes. So I'm focusing on two data sets in this talk, MNIST, which is probably the most famous data set easily, and then also a harder version of it called Fashion MNIST. The idea is you have some black and white grayscale image that belongs to one of 10 classes, either digits or clothing items. And the goal of the algorithm is to get the image and output a correct prediction of the class that it belongs to. So in this case, the function will be taking an X and outputting a vector, giving you probabilities for each of the 10 classes. Just an example here. That's the overall paradigm I'm working in. Okay, so thinking about machine learning on a quantum device, which is a very nascent but promising and a lot of buzz around an area of quantum computing, is how can we get a quantum computer to do machine learning? And probably, I think, still the most common way, or the most popular way of doing this is the variational quantum circuit. And the idea here is that you have sort of a very, very rough sketch of the circuit. The idea is you have some set of qubits, shows kets here. They, in some way, I'll talk about each of these steps in more detail. In some way, you encode your classical data, your vector of features, into that state via some set of gates. And then that goes into this very general variational quantum circuit. You have some unitary set. Those unitaries are parameterized by some set of parameters. And then you tune those parameters to get a state at the end that you measure and get some useful result out of. And that result can allow you to then optimize, go back in a loop, tune the parameters further, measure it again, tune further, and converge to some good solution to your problem. That's the very high up view of what this variational circuit algorithm does. So just to be more concrete, here go step by step. So the classical data encoding, this is in principle very general. You can take almost any way you can imagine to encode the data. You could do it this way, but in most practical, I'd say current research, you focus on generally rank 1 encodings where each feature is given its own qubit, and then you just encode the value of the feature in some rotation or some 1 qubit operation on that qubit. So this is not the only way you can do this, but it's very simple and very doable on modern hardware, or sorry, current hardware, I should say. Noisy hardware is hard to do very large gates. Just doing 1 qubit gates is quite simple to do. And so I would say, again, the most common way of doing this is start in your 0 state, you apply rotation around y, whose angle is given in some way by a normalized version of your feature. So take your feature x1, get it between 0 and 1, multiply times pi over 2, that becomes your angle of rotation to apply to your state. And that'll then in some way encode your data in some angle of this qubit. And then the overall state is the tensor product of those qubits all the way down to create overall rank 1 state. Suppose you have that state, that's a very simple state, it then goes in and gets modified by this very general quantum circuit, variational quantum circuit. Now, I've shown here at first is the big block, because in principle, it's just some general unitary. Of course, in practice, you have gates on your hardware. You have to be constrained in some way. I've shown here an example of just a set of 2 qubit gates that could combine to give rise to this overall circuit. The important part is not so much how they're arranged, but the idea that each one is parameterized by some theta, some angle rotation or whatever it might be. And these are the parameters you tune to get a better model. And so this is where the algorithm becomes challenging, because at first you had just your cosine and sine data rotation. That's easy to represent classically as a rank 1 tensor product. But generically, after you act on it with a circuit, you get some generic-ish state out. Not really truly generic if your circuit depth isn't too large, but much more complicated than your original rank 1 state. And this is what you then measure to get an output. So just to give a quick breakdown of this, the idea is that after you've featurized, after you've applied your parameterized unitary, you get out at the very end some state, then you measure some portion of the qubits that you had to get some set of outputs. So here I've just shown a simple example of 2 qubits being measured. So you have your qubits at the end, you choose 2 qubits to measure, and then you get out some bit string, right? Some 0 through 3 or bit string. And then that distribution, you measure this over and over and over again. You build a histogram of that. That distribution gives you the output of your function. Now, this is most natural for probabilities. If you have desire to model the probabilities of, for example, images, this is a very natural form. If you wanted to do more general regression, with negative numbers and stuff like that, it's a little more challenging. You have to maybe do some amplitude measurements. But just a general case, as long as you have your output desired to be between 0 and 1, this works just fine, right? Only downside is that it might require a lot of measurements to resolve differences between, small differences between the probabilities. Okay, so what I've shown here is, that's the circuit idea. Oh, yeah.
Just a question about that.
Yes.
In practice, are you imagining that what you're getting out are amplitudes and you just square them to get your probabilities?
No, in general, you would expect to get probabilities out because you just get some bit string outcome, and then a frequency, that frequencies of that over all frequencies give you some probability, right? So if I get, half the time I get this, half the time I get that, that's going to be some positive number inherently, right? Between 0 and 1. So amplitudes would require a little more work. You can still do that. You can do like a Hadamard test, something like that, to get a probability amplitude out. But the most simple way is just to get out a bit string, which is a probability. So you won't have the amplitudes easily. You can get them, but it's a little work to get them. And again, amplitudes make more sense if you want to have both positive and negative numbers, perhaps, or some, where it's not just as natural as having just probabilities as your output that you want. But classification tasks, probabilities are fine. And so it's very natural just to measure them directly and use that as your output. But you can further process it if you need to get a more varied kind of function. Okay, so that's the circuit idea. And as we've seen thus far, it's very natural to go from circuits to networks, right, to networks. And so what I've shown up top here is just the sort of symbolic view of what I just described. You have your density matrix in your 0 state, you rotate your data. So Ry is a data rotation. You then evolve the state with some generic U. Then you trace out some qubits you're not measuring. And then either you look at the diagonal elements or you measure in reality and get out distribution to give you your actual output, right? And so in terms of network, it's actually pretty simple. Left to right here, you have your vector 1, 0 for your 0 state. You just contract that with some 2x2 rotation gate parameterized by your feature value, and then you have some unitary that you have built in a reasonable way. You can track those in, in principle, track those in, and get some state psi out of that, and then you'll choose out qubits you want to measure, those you want to ignore. You trace out, you contract the ones you want to ignore on top here. Then you get out some reduced density matrix which encodes your final answer. That's sort of the high view, and this is all easily done via contractions, right? As you normally would map from quantum circuits to networks. Okay, so that's sort of the basic idea of how these quantum algorithms work, right? You have your data, you encode it, you have the gates you operate on, and you measure. But I think it's convenient, or it's insightful to take a step back and ask what's actually going on mathematically, because this will help us generalize beyond the quantum computing frame, just looking at general class of models that these fall under. And so looking at this, what are we actually doing? We have a function, right? The ith output, the ith probability value that we get out of this thing, right, is just the diagonal element, the ith element of your prime. So what is this thing? So, you basically what you're doing is taking some row that you encode your data into, and you're operating on it unitarily, then tracing over it, right? So I've shown here sort of these U's. I've grouped together for convenience the indices on this side, and then these two and these two to give a simpler unitary. So J is sort of all the input wires. K is the traced over wires. I is what you actually want to measure at the end. And then this guy gets applied to rho to give you some final rho prime. But really, you can do the trace first, right? You can do this part first and just get some big tensor W, right? Which just contracts with rho to give you some final output, rho II. And this is basically just an inner product, right? Between some tensor W, some tensor rho. I've written out here sort of what actually you get. You just get, the first element of rho times first element of W plus second element and so on and so forth, right? It's just some big linear regression problem, really, under all of the quantum fanciness. It's just assigning some weight to each element of rho and then adding them together, right? And so as an example of this, each element, basically your regressors, what you're regressing on are these complicated functions of your feature. So it's linear regression after you go from your feature to this cosine sine rotation state that you created in the first step, right? So it's linear regression on a very nonlinear function of your features. That's sort of the trick in a sense. And so just example of the rotation one, each regressor has some form like this. It's sort of a product of cosines and sines multiplied together of each feature type. Right? This is one example of the different regressors you have here. So it's almost sort of like a partial Fourier basis sort of transformation. Not quite true, but it's definitely not a simple linear regression on X. It's much more complicated than that. Okay, so with that in mind, you can sort of start to describe what generic tensor regression looks like outside of the quantum context. So as I mentioned earlier, there are two steps to this process. The first is featurization. So you have your X's and you encode them in some rank 1 tensor, right? In the case of the quantum state, it was rotations. It was rotating into cosine and sines, then multiplying them together. But in general, one can imagine anything you want, right? There's no real constraint that has to be L2 normalized, has to be rotation based at all, right? It can be anything you want generically. And so, examples that you see commonly are map X to some polynomial of X, some power of X, some set of powers of X, map it into some L1 normalized state instead of L2 normalized if you wanted to, or map just to, to cosine and sine if you wanted to, right? Generically, you can do anything you want. Or quantumly, you have to sort of at least obey L2 normalization to be a valid quantum state. And the regression in the quantum case, it has to be some kind of like traced over unitary operation, right? Because quantum mechanics is unitary. But generically, it can be anything you want. W is unconstrained generically. And that's why I said the quantum case is really a particular kind of this broader idea, which is first featurize in a complicated way, and then just regression, run regression on that complicated featurization. That's the paradigm, really, in a nutshell. As simple as that, really. Okay, but there's sort of an issue with just doing this generically. Yes.
I'm just trying to kind of parse.
Yeah, please.
How differently that one slide sounds very much similar to what I've heard said about kernel methods generally. So is it always going to be nonlinear, or is there some guideline to
So always
some
good to.
nonlinearities to be more powerful?
Well, I think that, I mean, certainly going beyond linear regression is pretty important, just because it's, for certain kinds of problems, most kind of problems, it's not powerful enough to get separation in the way you want, to classify images, for example. Linear regression is not very good at doing that. So you want to go beyond just some scalar times feature plus scalar feature over and over again. That's not powerful enough to learn complicated problems. We know that from experience. You have to go beyond that somehow. So one way of going beyond it is to first featureize, construct regressors that are complicated functions of the features originally, then regress on those, right? That's sort of necessary to go beyond the linear regression paradigm, right? You usually just can't do enough with just linear regression on X directly. That makes sense? Is that what your question was? Maybe not quite.
I think there's a formulation of variational quantum algorithms that is shown to be the same thing as kernel methods. So yeah, you could rephrase all of this and just get back to kernel method framework. Right?
Yeah,
this looks
possibly.
like kernel
Well,
methods.
SVMs are going to come up soon. There's a little bit difference, but some difference. Yes, generally speaking, yes, there's a lot of similarities.
Right.
Yes.
Maybe less slides about this, but does your own work kind of answer part of Ian's question where you did this other recent study of figuring out like which features are actually being used well by Tensor?
Yeah, I'll get cover that for sure. Yeah.
And other features are kind of just like neglected or not used very well.
Yeah, there's
Maybe this could cause like an interplay of better design to.
definitely there's a sense in which or you can be pretty sure, just in common sense wise, that probably not every feature like this is going to be useful intelligently by the model. Like there's a ton of these, and 2 to the power of features, you have 100 features, there's 2 to the 100 of these. Are they all going to be useful? I doubt it, and I'll talk later on about how you can show that's not really true. But certainly you need at least some of those. Just a linear one is not enough. It'll be as weak as linear regression is, which is weak for complicated problems almost always. So you need some nonlinearity in there. You need all of this there, all of this, perhaps not.
Sorry, are there simple examples of nonlinearity that make things worse than linear, or maybe nonlinearity?
If the problem is linear, it would be worse to have nonlinearities. That would be true, I think. You'll get more noise or more variance on solving the problem. I don't know if, like, assuming you have a reasonably complicated, data you need to separate, it's hard to imagine it being worse than linear regression. But maybe I'm not going to say it can't be ever. Probably you could find an example where it does worse. But if you're not linear, then you want to go beyond linear almost always. Yeah, the honest one is, if it is linear actually, then it will only be worse to include, on average, worse to include. Right. Yeah. Other questions about this?
Then you're taking tensor product after you do those formulas in the boxes. Then you're
Right. Each feature goes to one of these guys. Then the overall X, the big inputs that you overlap with W, that is that's a product of all of these guys, right? So each element of X is a product taken from every one of these guys somewhere. The first point of X1, second point of X2, and so on. That whole product is how you get something like this. That whole product is one regressor in the overall regression scheme. Yeah. So they're very powerful eventually, but they're also very complicated, very big. And there's potentially problems that can arise if they're too big. Okay, questions other than that? Yeah.
You have an efficient way of determining which functions can be learned effectively using this.
Ooh. Well, so I mean, certainly you could, if you have a function that literally is built off of regressors that happen to be given by this thing, then it's great. But I think that you could do some sort of Taylor expansion to see what kinds of powers are most important. The biggest problem is that generically for most learning tasks, the function is unknown to you entirely. What is the function that classifies MNIST? Who knows, right? So I think that if you had that sort of access where you actually know the functional form pretty well, then certainly you could definitely be more fine-tuned here. You could try to find rank 1 structures that have most of those things in them, right?
No, I know what I'm saying is
Yeah.
the other way around. If you have
Okay.
a circuit, and you
Yeah.
want to know which functions the circuit estimates well. Because if you phrase this in terms of kernel methods, you have a mathematical framework to do that, and like in decomposition. But if you just do it in terms of VQA, is there a way? If I just give you a circuit, and I tell you what functions can be approximated well with this circuit.
I wouldn't know. No, I'm not sure if you can.
That
I
would
mean-
be very useful to me to find out.
Yeah, I'll keep that in mind. I don't know of any, especially if it's a big variational circuit, what the class of functions it actually is able to capture well really is in a meaningful way. It seems too black boxish almost to be able to pick it apart like that. But
Say things about the size of the Hilbert space, right?
you could say that, but I'm not sure if how that maps to like a typical problem in machine learning, how the Hilbert space size would map convincingly to a kind of classical function you want to model, but I'm not sure. It's an interesting question. Yeah, we'll think about that a little more. Okay, anything else? Okay, so I'm going to begin to try to incorporate tensor networks into this, but it'll be somewhat misleading. And I'll come back to how it's misleading a little bit later on, but it will suffice for now. So the biggest problem or obvious problem that you have is parameter numbers, right? So X is actually okay, because X, we made rank 1 from the get-go. So it, parameter-wise, actually very fine to hold in memory, for example. If you want to do this classically, you can hold M times, in this case, M is number of features. P plus 1 is the size of the vector. So M times that is pretty manageable, unless you're huge. But W, different story. W, in principle, unconstrained, totally arbitrary, has exponential number with the features of parameters. And so you can't hold that in memory. You can't work with it practically on a computer or even a quantum device. For generic W, probably that would be too large. So you choose to represent W as some network of smaller pieces, right? That's sort of the recurring theme throughout this symposium. I'm just sort of showing here examples of this in practice. People have done machine learning with MPS states. That was actually one of the first, probably the most common still network types to use. Also use trees. This is also fairly popular. Also simple to do classically because it sort of remains separate, not entangled the whole way. But also people have done it with something like Mira, which is a more complicated network, using more clever extraction schemes and approximations. And so all of these are solving the same basic problem, which is W is too big. Let's make it much smaller, shrink it down, and then let's work with those components in the network instead of the components of W directly, because there are just too many of them. Okay, so we talked briefly about the model pipeline, just to give a broad sense of how this would work in practice. So first thing you do is get data set, MNIST in this case, right? Then in parallel, you choose network type. And I have this sort of like dashed gray question mark line, which suggests that there should be, in principle, a way to use the data set you want to solve to choose the best network type, but that remains open problem. It's not obvious what kind of network is most appropriate to solve a given machine learning task. It'd be nice if there was a clear answer to that, and there's maybe some directions that seem promising potentially, but it remains very much open how you can go from data set to most appropriate network type. For the most part, people choose networks based on just ease of use. Is it easy to contract on my computer? Then we'll use that instead, right? It's not like the network you choose has been fine-tuned and tailored to be best for your data set. There's no real rules thus far that have shown themselves to be very effective for going from data set to network type. But once you choose a network type, the biggest hyperparameter that you want to set is the bond dimension. That sets the number of parameters you have, and it's determines sense how powerful, vaguely speaking, your network is. And then from the other side, you choose some functions, call them H here, the feature functions that you featureize your variable into, or your feature into, to make your rank 1 data X tensor. Once you have those together, you just put them in together into this network here, the MPS on top, the rank 1 on the bottom, and then you just contract it together in a efficient way, depending on network type. Then you get your output from that. You usually have some, if it's a vector output, you have some free leg not contracted over. That will determine the elements of your output. You compute the loss function from that. Could be L2 loss, could be a variety of things. You then optimize that in some manner. Personally, I tend to use just gradient descent, atom or RMS prop. There have been other methodologies, DMRG style, where you sort of contract everything else but one of them, optimize those one parameters on their own, and sort of sweep back and forth across. So each tensor is optimized individually, then you converge in the long term to some results. So other ways as well. Most of them seem to work roughly as well. Yeah.
Using this, don't you get bare plateau issues?
So often, yes.
Can you repeat the question?
Oh, right. So the question was, don't you often get barren plateau problems in this sort of setup? And the answer is often, yes, but not always. And
Could you specify it often? I played with it and I got like 99.9999% of runs ending up in bare plateau.
interesting. So one thing that you find in practice, I don't have a slide on this, is how you initialize the tensors is very important, because if you initialize them somewhat randomly, like if you think that, imagine you had like 100 of these guys all together, and the typical norm of the matrices in the MPS was large, you would get a huge, massive value, right? If you put all 100 together in one, when you track them together to get one output, the average norm of this guy would be huge, right? Because your contributions from all the matrices have norm greater than 1 all together. Alternatively, if norm is less than 1 come together, you get 0 very quickly, right? Because you have 100 matrices all with small norms all together gives you a very small output. So one of the key things to avoid random plateaus is to initialize close to a stable sort of point in the network. For MPSs, if you have the slices of your tensor here be identity matrix, something close to that, then you get a very stable contraction because you have norm 1 on 1 on 1. The overall fraction of identity matrices is identity matrix again. So then you take that and you modify it slightly around that point. That's a stable starting point to work with, and you will avoid issues of random plateaus if you do that. So I think that the answer to that question is you have to initialize cleverly. You can't use poorly sort of conditioned matrices.
And also the gradient itself, do you, what's your method for grading it? Phase shift?
In practice, yes. Like if you're on an actual quantum device, yes. On a computer, you just look at the actual gradients themselves. You use TensorFlow or some automatic transition algorithm. But yeah, for a quantum device, you have to actually measure it and then get an expectation value, get the gradient from the unitaries from that, and so on. That tends to be somewhat on the back burner of people's minds. Like that's the last thing to worry about. Once you do the exact one first, if it works there, then try the actual way to do it. So I've mostly focused on just idealized gradient descent, not worrying about actually doing it on a real device. But people who are wise to that should look at that carefully, because that's a whole other issue. Can you get good gradient values based on measurements at a reasonable number? That's a problem. All right. And then you just do this in a loop, and eventually you'll converge, as far as you're willing to go, either overfit or you'll converge to a good solution. And that's your sort of final model that you use then onward. So questions about this overall pipeline here. This is just a general flow for how you would do these kind of models, with keeping in mind this notion of how you initialize tensors can be very important to making it train properly.
So are you putting in all your data over and over, or are you doing this in batches, or typically like this doesn't look like you're looping over data in your dynamo.
Oh yeah, so basically the contraction, this is a bit maybe cartoonish. Really what you do is you would contract. Yeah, I do it in mini batches in practice because I can, and it's on a classical device. On a quantum device, there are no batches, as far as I know. You'd have to do it each one directly on its own. Again, that's one of those things where it's, you do it ideally on your computer. In reality, you have gradient problems. You have no batches anymore problems. That's all for the people later on to figure out, I guess. But as I would do it, I would do many batches. So I would take maybe 100, maybe 100, some power of 2, ideally, or something like that. Do a contraction of those. Use the loss of that set as one optimization step, and then just go through the data set like that over and over again. So you slowly work your way through all the data over and over again. But you do each of these loops in a small piece. 100 or so, samples in it. That tends to make better for the gradient. It makes it smoother. Doing one sample at a time is doable. It's just slow, and you have some noise problems a bit with the gradient, but it works okay if you're patient with it. Yeah.
How badly does trainability and like variant plateau questions and related stuff depend on the featurization of the data? Because I imagine that if you're trying to learn a function that has certain symmetries and you only give it features that don't respect those symmetries, it's all just going to be mumbo jumbo right at the end of the day. So like it's a question of inductive bias that needs to get baked into featurization is how I see it. Is that true, or
I think that
some science around that?
Apparently, there is no science as far as we have to go, at the very least, you know the global sort of span of your space. You know that if I have, the polynomial regression of powers, at best, I get some function in the sort of space of those powers. But that's impossible because you get anything else there, right? Is that good enough for your problem? Who knows? Often hard to say. If you knew your function outright, you'd be smarter about it. One thing I would say is that in practice, you tend to not assume that you have baked in a very strong bias initially, because often you just can't afford to do that. You don't know what the bias should be. If you knew, which is a rare problem in classical machine learning, could be common in certain kinds of problems, like physics problems, perhaps, then you definitely should include that somehow. But I don't really have much experience doing that encoding it that way.
Specific example is
Yeah.
about symmetries. If you're trying to learn a
Yeah.
function that you know has some specific,
Right.
in physics, if you do it with actual neural networks, what you would do is if you know that you're trying to learn, like say, a rotationally symmetric things, you would only give it scalar products of vectors that need to go into that network, and therefore it can like learn that stuff efficiently.
Right.
So if you know some high level information about your function, I guess that featurization might depend on that stuff as well.
Certainly, yes. I mean, if you can describe your desired function in some way like that, you absolutely would be stupid not to try to incorporate it somehow into your thing, right? Problems I've worked on don't have that property at all, but they just don't, they're not knowable in any way like that. But if you knew, then not only could you constrain the features, also constrain your core tensors as well, right? If you know that feature I or J should behave very similarly, you can enforce some symmetry in the elements of your tensors as well, right? MPSs do this, and commonly have, you have periodic conditions, something like that. You can force the cores to share weights in some way, right? So that would be an extra way you can enforce known symmetries. But I personally work on problems where I had that either luxury or challenge, depending on how you view it, of that.
Sorry,
Keep going.
I only mentioned it because the barren plateaus were brought up. So I
Yeah.
mentioned that if you give it features that are irrelevant, then all of the weights related to those features would have zero weight.
It'll just give you sort of noise. Yes. That seems like, one way out of it would be to narrow your problem in some way. Yeah.
There is one result that's been used for quantum phase transition, specifically that, and yeah, if you do it's called the inductive bias in quantum machine learning, the paper. So yeah, you could do that, but as you said, it's a very, very small subset of problems that the inductive bias will force.
Yeah. Yeah, I think
But
that
it works 100% accuracy when you know.
Yeah, when you know the solution.
Yeah. I mean, you can learn it easily.
that's the problem. I think that overall, though, to your point, I think it's definitely been understudied how you should really choose your featurizations and these H functions. People have just sort of throwing things out that seem reasonable. The cosine and sine was sort of quantum inspired. The polynomial one is just sort of, it seems reasonable because products of features are more powerful. I would say there's been no real principled study of how you choose your sort of H functions here, how you featurize from your feature to your vector of things. And I think that symmetries would be an obvious starting point to be able to say something about that, how you should choose that. But I know of no work that's done that as far as I know. Yeah.
Well, if you think, the way I sometimes think of that, like cosine sine.
Yeah.
It's kind of like choosing 1 and x, practically.
In like a small x limit?
Well, like if x is small, it's like choosing 1 and x.
Yeah.
But, if you have 1 and x for your input, 1x1, 1x2, 1x3,
Mhm.
then what you're doing in this large, after you take the tensor product,
Right.
is you're adding all linear features, all quadratic features. And so in that way, it's sort of,
Yeah.
it's like a kind of, you're throwing in all the features that you can think of.
Although you lose the squared powers. So you only have like multilinear. You don't have any.
Yeah.
So it's like a quadratic-ish, but like only multilinear quadratic. It's not fully quadratic. So you have to add those in sort of vertically, add to your vector. And there's some problems there if you have a lot of them. You have a lot of then weights in your coordinates, or if it becomes a problem. But yeah, you have quadratic-ish. But why is that good? Like, why really is that useful? It just sort of is. In practice, it's good enough to solve a lot of problems. But really, why it's good enough is hard to just say in particular, right? Just in practice, we've tried it. It worked. Great. I wish we knew really why or how we go better. How we get better is the biggest thing. How can we improve upon that in a principled way? I don't know. Adding in quadratic terms could help, but why? Well, Taylor's theorem, maybe you could sort of appeal to that, perhaps.
In another direction, I guess the question is, do you ever deal with discrete data where you're not really featurizing at all? You're just putting in 0 as 1, 0 and 1 as 0, 1.
Oh, like a binary data?
You're still doing this optimizing.
Definitely, you can put in discrete data for sure and encode that in a similar way. Actually, I'll have a slide that talks about that a little bit and some interesting things that happen when you do that. But yeah, you can absolutely do this with discrete data. And you couldn't, I think actually there's a paper that tried to think about if you just encoded like one hot encoding, you had inherently discrete data, you just give every data point its own vector position. And then there's, how does that form? Okay, it turns out, but yeah, so discrete data doesn't pose any real problem to this approach. You can either choose to put it in the same way you did it before, or you can one hot encode it in as its own discrete layer, whichever one does best. But again, how you decide which one is better and which one's worse beyond just trying it out, I don't know. trial and error seems to be the best way to go forward for these things, unfortunately, at the moment. All right. Questions about this? No, yes, no. Okay, so there was talking about this before. So there's comparisons you can draw to SVMs or kernel learning. So just to summarize, SVMs, the idea is you want to have your data, shown plots here. You want to separate out data. I think it shows sort of black is one class, white is the other class, and you want to create some straight line, ideally, through your data. But just to create a hyperplane that separates the data. But most data is not nice separable in hyperplane. You can't draw a straight line through data and get nice clean division. But you can transform data in some way where it becomes separable by a straight line. That's one of the key ideas behind SVM learning. And so I just sort of shown here in just very vague terms what's going on. The idea is that you have some X, you featureize, like I showed before in the tensor network model case, you have some function here that goes to a higher space. And then what you're seeing is overlaps between samples. In that space is given by some function K. So X, just X dot X, but phi dot phi is some function we call K, called the kernel. Right? And this SVMs, this is really the key thing. Implicitly, K defines some phi, but really the K is the important thing. If K is doable in a simple way, that's what defines the SVM's nature. And it's an example of this. If you had to encode like quadratic features, right, you could have the overlap of this be something akin to just the dot product of the features plus 1 squared. That will give you up to maybe some extra coefficients, roughly speaking, the overlap between two of these phi terms. So you have to actually compute the actual vector inner product between two phi's. You can just compute this guy, the regular inner product, then just add 1 and square it. So K gives you a shortcut to computing the overlaps between featureized versions of X. That's sort of the punchline. And that's very similar to what I've described so far, right? And these are models, right? The key difference to me, though, what I'm really curious about, if people's thoughts about this, is it seems like SVMs, by their very nature, construct weight matrices that are always linear combinations of some portion of the data set. The support vector machine, support vector, refers to some set of vectors that are used to construct W. So W is just some sum of weights times the featureized sample. Right? And this becomes, if you had a rank 1 fixation, it would be something like this, like sum over rank 1, stuff like this. But that is not what the tensor network does. It does not propose or report to have W be a linear combination of samples in any way, shape, or form, right? And so this is where I think SVMs diverge from tensor networks, is that they are not, W is not constructed in this arguably principled way, but also maybe somewhat limited way, where it must be some linear combination of portionary samples, either all of them or some subset of them. And I think that idea, to me, is interesting. I think it deserves further discussion, because I mentioned before that I was being a little misleading about how I talked about the role of the network itself in these models. Is that usually when we discuss these, we sort of present them as if they're necessary evils. Like we have W, but it's so big, we can't hold it in memory. So we have to appeal to networks that are smaller to work, right? But I think it's actually not really correct, because even if we had a computer that could hold all of W exactly, no need to truncate or constrain itself, we want to use W on its own. And the reason for that is pretty simple, actually. It's because the overlaps between samples, when you featureize into X, the rank 1 tensor product, tend to be suppressed extremely heavily. If you look about this, imagine we had X in this sort of, featurized into some, let's say, normalized form. So X is a norm 1, which means all of the vectors that make it up are norm 1. Then the inner product between rank 1 X and rank 1 X prime is a product of like 784 for MNIST. That's how many pixels there are in MNIST of these guys together, which is some average cosine angle to the power of 784. Now, cosine is 1 between 1 and 0, or 0 and 1. That to a power like this is almost always 0. Unless you're very, very close to 1. This will be almost 0 by the end of this inner product here. And what that ends up doing is it means that if you have a W, like the SVM case, which is a linear combination of samples, then the inner product you're going to get out of that is going to be almost 0. And in fact, you can make it exactly 0 if you want, because you can imagine, as John talked about, what if you had binary data? You encode it only into 1, 0 or 0, 1, right? In that case, unless every pixel in your image is the same, the overlap between the two samples is 0, because only one case where you have 1, 0 times 0, 1, that inner product is 0, so the whole thing is 0, right? And what happens is that if you make W, if you have data like that, you can make W be exactly perfect by doing a linear combination of your x's with the label you want to actually solve for divided by the norm squared, right? If you take an inner product of your training set with this guy and they're all orthogonal to one another, you get exactly the right answer, loss of 0, right? But you'll be able to generalize horribly because every new sample you put in, we are orthogonal to all these guys. And so you get nothing, right? So W is, you need to have some structure on W to interpolate to unseen data, right? You can't just use W on its own because the optimal W will be almost entirely ignorant of data outside your training set. I think a point is not brought up enough, is that it's not just memory being too small. It's that your sample size is too small. You must have some way of guessing in a clever way what a new sample looks like. And W can't do that. It's too unconstrained to do that. That's sort of the point I guess I want to make. Questions about that idea? Disagreements with that idea? I don't know. So SVMs to me are sort of, they're more in this linear combination frame. And so they, I think, would struggle with featureizations that are almost orthogonal or actually literally orthogonal to one another. They can't really adapt to that, that kind of frame, or at least it's hard. I'm not sure I know of any SVMs that don't operate like this, where you need to have some overlap with other samples. Whereas you could have MPS learn this binary problem, no problem. You wouldn't actually notice even that it's been made this way because it does not assume, that you have to have overlaps between different samples. Okay, so that's sort of an introduction. Which do I have here? Oh, okay. Shoot, I gotta run. So this is actually just an introduction to what I actually want to talk about. That was the overview of how these models work. So I was interested in particular about these in regards to how this sort of feature space is used, right? Because we know that X here is huge, right? That was the whole point of this. And so X lives in a feature space that is exponentially large in number of features you have. And so that's useful because it gives you more, more powerful regressions to work with, right? Linear regression, just bias and xi is weak. If you incorporate more features, for example, all multilinear features, all products of features, for example, that's more powerful, but also more of them to work with, right? Similarly, sinusoidal functions, they're also more powerful than just linear functions. So this feature space is obviously useful. It's giving you more power, right? And you can see that obviously here, just in case anybody doubts that, right? It's well-known problem in separation where you have this XOR, where you have red and blue two classes. You want to create one line that separates blue and red, but you can't do that when they're arranged this way, right? But if you add one more feature, add XY feature, then it separates trivially. So having interactions, products of features is obviously valuable. It allows you to, represent more complicated functions. But going back to the previous question that was asked, sort of, we have talking about 2 to the power of a huge space. How much of that is actually being used by the model? Can we remove parts of the complexity in some way, in a variety of ways, and still achieve basically the same level of accuracy? That's sort of the key question I want to ask. Do we need the entire space, or is only some of it enough? And so I have sort of 2 different works that probe this. One is a quantum one, which looks at if you remove the coherence of the model, if you make it less quantum, how much you actually lose in the performance of the model. And the second one is if you remove some of these features here of the space, how much performance do you lose in the model? So I'll start with the quantum one. So removing quantumness is maybe somewhat of a vague term. I'm going to define it here more rigorously. For us, we mean take rho in some basis, z basis generically, and remove, decohere, dephase, remove the orthogonal elements of these, only preserve a diagonal, right? That in principle makes rho behave as if it were just a distribution of sort of z basis bit strings. You had some computer just giving you out random z basis states. That's what is, this rho without any orthogonals looks like, or how it behaves like. So that's what we're going to do. We're going to take rho and we're going to remove or reduce, because I have down here, also reduce by some you can go in the middle. You can have just a reduction in the size of these without actually getting rid of them entirely. So if you remove the magnitude of these somewhat or entirely, how much of the model, how much performance do you lose? That's what I'm curious about. Okay, so what does that mean? Just in practice, you can do that pretty easily. You can remove the orthogonal elements of a qubit by using cross operators, just these 2 here actually. So the idea is that you use K1, which is some proportional to the identity matrix, K2, which is some sigma z proportional. You just take rho and you just add together this sort of sandwiching of K1 and K2 here, you get a decohered or dephased rho by gamma. Right? Gamma is 0, you have no dephasing at all. Sorry, gamma is 0, you have total dephasing. Gamma is 1, you have no dephasing. And so one thing we had to ask ourselves a little bit though is, what does this look like when you have more than one qubit? So we had to sort of choose how you want to decohere. If you just take tensor products of one qubit dephasing or decohering, you end up with actually a non-uniform sort of penalty on the terms. Some terms have no penalty at all. Some have just one copy of gamma. Some have two copies of gamma. And you'll go beyond that if you go higher number of qubits. Or you can imagine removing all of them uniformly, right? It's also a valid way of removing quantumness from a state. We decided that it's more realistic to have noise channels that are tensor products of one another, because that doesn't require you to have, like this one here requires you to have sort of like clever noise, which works together on multiple qubits to get uniform reduction. This guy's just, each qubit is on its own, and together they have this form. So we chose this form for decohering. Okay, so if we imagine now, what is that like for a network itself? Basically you can imagine doing this as just some super operator acting on rho. So you take rho, act on it with some also fourth order tensor, and you get out rho prime. So it's actually pretty easy to incorporate into a network. You just take your network, we use a tree in this case, and you insert in these guys in between the qubits and also between every layer. So every layer is decohered, basically, is our setup. And this will basically model if you have a lot of noise in your system, right? They tended to remove coherences, but left the overall Z probability the same. That's a pretty common kind of noise to have in quantum devices. How much does that noise affect the performance of the model? That's what we're trying to get at. Okay, so what does that mean in terms of regression? So all you're really doing, actually, it's not complicated. Basically, you have your overall data input. You tensor product of these one qubit rows, right? These matrices. And so the full regressor, I'm using in this case, 2 qubit example, is just going to be products of elements from all these guys individually. And so basically you have some regressors that are only products of diagonal elements. Those guys are totally left alone, right? You have some which are have one contribution diagonal, one's off diagonal. Those guys have one penalty of gamma. You have the ones that are off diagonal together. Those have 3 penalties and so on. And so basically some regressors which utilize off diagonal elements are reduced much more than others. So you sort of have like a hierarchy of terms where the more off diagonal you are, the more steadily you are reduced. And in the limit of gamma equaling 0, only one that survives are diagonal elements. But if gamma is non-zero, you have some contribution from the higher order terms as well. Just less of it, the more off diagonal you are. It's worth noting, just as a side point, that if you do fully decohere, if gamma is equal to 0, and you remove all of these guys, you should recover a Bayesian update rule. Basically, you go from probabilities to probabilities, and you can rewrite this expression here as just some Bayesian update, where you have some posterior, some prior, and you basically just sum over some unitary that's squared, so it becomes positive, and you end up with just some sort of Markov update, Bayesian update rule. Okay, so what did we do? The task was basically MNIST / MNIST. Because of the limits of computational power, we chose to shrink it down. So usually MNIST is 20 by 28. We went down to 8 by 8. So the problem is doable but harder. You can see visually here, it's not as easy to make out what these are anymore. But they're still solvable. It's still a reasonable problem. You can definitely solve it to some extent, but it's harder in some ways. And so what we did is we encode each pixel onto 64 qubits. This is all software. Hardware, none of this actual device. Don't get carried away here. And then we initialized our tree. We then had different rates of decoherence. We decided to not do 10 class classification. It was measurement was just a bit too much. So we had to sort of group together the classes into 2 groups. And the goal was to divide those 2 groups up. So maybe, 0 through, maybe half of them would be in one class, 0 through 5, other 10 the other class, and so on. So just some arbitrary division in 2 groups allows us to more easily measure our qubits. And then we created the accuracy after we trained the network. Okay, so this is a plot showing our results. So the dashed line up top here is the sort of state-of-the-art convolutional network. So this is sort of a best case classical machine learning scenario. Obviously, it's better than we are because we're using 2 qubits, or 1 qubit for each sort of leg of our tensor. So it's pretty low rank. And the red here shows fashion MNIST, which is a hard data set. Orange here is MNIST. And so what we see here is pretty obvious in some sense. As you decohere, it gets worse, which we'd hope is true, because that implies that we are actually using the quantumness in some way. We wouldn't get just as good performance if we removed it entirely. But perhaps the decrease is not very large, especially as you get beyond a certain threshold. Once you get beyond like 0.2, moving it further, MNIST is pretty non-important. So one can maybe perhaps infer here that the biggest loss comes early on. You lose a little bit of coherence, you've lost a lot of the advantage. And then beyond that, There's some loss still, randomness more so, but the steepest drop off happens early on, which is not great because that implies that if you can't get almost all of it, there's not much value in having the rest of it in some sense. We'll talk about it in more detail. Okay, so that's pretty obvious. Not very surprising. Decoherent network does worse. Great. But what if we decide to offset our noise with more qubits? So more noisy qubits go in. They're still bad qubits, but there's more of them. Right? Is that in some way allow us to offset the losses from being decohered? So what we did is we took our unitary, which before was just 2 qubits go in, 1 goes out, 1 is traced over. And we just put in extra qubits, ancillary qubits in, always initialized to the 0 state. Put them in, 2 get traced over, 2 go out. So a little bit of a thicker model, higher rank. Do we undo some of the loss we had, even with noise? That was the question we wanted to answer. And the answer is yes. Kind of somewhat sad, actually. If you have 0 ancilla, right, which I had shown before, you have this clear loss. You add more decoherence, you lose performance. Right? It actually goes down. But if you add a qubit, the green line here is 1 ancilla qubit, and you fully decohere the entire thing, it's better than a fully coherent 1 qubit system. Which means that if you had no quantumness at all, basically, you just add another ancilla, it's also totally not quantum, you get back all your performance. Right? Now, to be fair, it's still better to have 1 ancilla fully cohered, but the drop off is not as big. You lose some, not a ton. And eventually, of course, with 1 ancilla, there's some diminishing returns where if you have like 3 ancilla, there's no real point going beyond that. But each one shows a similar behavior where there's a loss, but it plateaus pretty early on. Right? So in that sense, it seems like just getting a high enough rank in your network is almost high enough bond dimension, almost worth losing all coherence, which is somewhat surprising result. Yeah.
Well, yeah, 1 qubit, right? You don't use it. You don't do anything with your features with it. Let's say for the first one, the green one.
Like this one here, like we're adding in, yeah.
It's still better the performance with no decoherence in it.
Oh, so ask that again, make sure I understood what you're saying. You're asking.
You're no decoherence, you're just adding a random qubit, it still betters the performance from what I'm seeing.
Well, it's not a random, it's a qubit that is initialized to 0 and then is carried through the rest of the operation, right? So it extends sort of, you have now 2 going forward instead of 1. So the very least is a higher rank tensor network now. So that, it's not shocking that it's true, but it is somewhat surprising that the coherence becomes less important pretty fast, which we would have necessarily not wanted to see that because that implies the quantumness is not showing through that strongly. It's somewhat a vague, conclusion raw, but it's sort of best we can do at this point. For whatever reason, that extra Hilbert space dynamics just is not doing as much, and we can't find it very well. And that's sort of one of the things I want to draw from this is that the quantumness is important in the sense that it gives you a better result, but it draws up pretty fast. You can add ancilla and undo the damage pretty easily, right? And also adding more ancilla isn't necessarily obviously better. 3 ancilla here is shown as blue here is marginally better than 2 ancilla, even actually worse a little bit over here. So pretty clearly there's a drop off in value of adding more ancilla, either coherent or not coherent. So one problem is also sort of illustrates is how do we improve our models beyond this? Adding more ancilla is good only so far. Beyond that, it seems like it's hard to improve any further. And then, coherence itself is valuable maybe, but not as valuable as you might want to have assumed, given this is supposed to be quantum machine learning, supposed to be, quantum is very important. But fully decohered, it does almost as well in some cases. Okay, so I have barely any time at all to cover the second half of this. So do it fast because it's interesting. So, okay, that was the quantum case. The classical case is a bit simpler in some way. Basically, imagine we took this kind of featurization. Every feature mapped to 1 and x1. This was actually mentioned by John in the question previously. That gives us a regression, which is basically taking every possible feature product and using that as our basis for regression. So it's simple, basically you sum over all possible, if I is 0, you have just 1 here, so it doesn't contribute. So you have the bias term, all linear terms, all pairs term, all triple terms, and so on. That's the basis we're using. There's 2 to the m of those total. So it's a big space if all of it is being used, big space. And what I'm interested in is how does the degree, which is a number of products, of features in your product, how does the degree of feature product influence the utility or usefulness of those regressors in your overall model? That's the question. And I'm just going to skip this entirely. It's all it's saying basically is that, well, I should skip the top of this. So the top of this says that it's possible to contract a model where it separates out the different degree contributions. This is not trivial, but you can show it's possible. Basically, you can have your network contracted together and get a vector out, which separates out all of the degree 0 terms, degree 1 terms, and so on. So for example, here I'm showing this sum over these degree terms. The second degree term is just all of the pairwise products, right? Some of all of those. So you can get, there's a way of contracting networks together, which gives you these guys for free, for free, but for relatively cheap, where it's not that hard to get these out. Once you have those, let's skip this entirely. Once you have those, you can then take your model and see how well it performs only using some of those degrees. That's sort of the key idea. And so what we did is we took 2 network types, tensor ring, which is MPS, which is sort of a looped end. It's easier to contract, really. That's the reason why we used it over an MPS, and then a tree as well. 2 models. We trained the 10 of those each time, and we just looked at how adding in degrees, or how different degrees behave in the model. So first thing we looked at is the magnitude of interaction. They're saying how big is the contribution, of each of these D terms. How big are these guys overall? That's right. On the bottom here, we have degree, top of magnitude, average magnitude. And so what we see is sort of this sort of a hill shape, right? Where start out pretty small. There's sort of a peak at about maybe 20, and then you drop off pretty largely, right? Which is not surprising. So, the largest possible product is all 64 features together. Those are almost entirely unnoticeable. They're so small relative to the other ones. So we know just from this alone that the really, really high degrees can't help you. There's just not enough of them to change the output of the model, right? But, up to about 30 or 40, maybe, right? Maybe these guys could be useful, right? So the magnitude gives you some notion that the very high ones are not going to be useful at all, but up to 40, which is still pretty big, could be useful. But now look at the accuracy. So now what we did is looked at, if you look at the model and you just keep either each degree on its own or the cumulative sum up to some highest degree, how accurate is the output? So on the dotted lines here, we show the individual accuracies. So take each degree on its own. How accurate is it? The answer is not very accurate. It's up to maybe half at best, but higher degrees are almost 0 or almost random guessing, basically. And that's even more true for randomness down here. So each individually, the degrees are not very good at all at doing classification, right? The cumulative, which is a solid line here, shows that if you get up to, up to about 10 or 20, you're going to reach the maximum value. Anything beyond that doesn't improve the performance of the model at all. Now, that's less true for randomness. Here, the plateauing happens later, but still there's some plateauing effect where eventually, high enough degree, you just can't get any more performance out of it. But also, you also see that the lower degrees are not very good at all either. If you only add up the first 10, let's say on this case, you're almost as good as guessing, right? So you need to have almost all the way up to 30 or 40 to get the full accuracy. So when we train a model on all the degrees, it clearly needs to utilize at least up to 40 to get out its full potential, right? If you train on all of them at once. That's sort of what this is showing. So a typical model, when trained, will use a large portion of the degrees, right? It only plateaus a very high number, right? So before that, you improve as you add more in. But what if we decided to train model explicitly only on some portion of the degrees, right? So we optimize the parameters specifically to do well when constrained to only a small portion. This is the key sort of point. We had 2 different types of these. So the cumulative one takes all of the degrees up to some point. The individual one just takes each degree separately, trains it on its own. And just to make sure we're all clear here. So the degree cases, degree 1 has just linear regression terms. Degree 2 is products. Degree 3 is triplets. The cumulative one is up to single, so it includes the bias term up. Cumulative 2 is the single terms and double terms all together. And cumulative 3 is the entire thing on its own. So the cumulative ones include all lower ones. The degree ones are just individually done. And here it's interesting. So we show here this dark line was the previous result. This is how the model performed when trained on all of them and then analyzed separately. But here, the orange and blue lines, they show what happens if you train the model only on a small portion that you're going to use. And the result is that actually they do almost as well as the entire one, up to MNIST up to maybe degree 4 or 5. You've already recovered the entire performance. Dashed line here shows the overall model performance on all of them. So you match that performance on only a small fraction of them. That's surprising somewhat. It means that the network uses them when trained on all of them, but it's not using them in a unique or powerful way. Because if you train the model to only use a small portion of them, it's almost as good, right? It's almost as good, or even better in some cases, than the full model. That's true of MNIST and batch MNIST. Here, the blue line almost reaches the actual full model only using 10 degrees out of 64. So clearly the higher ones here are not giving you unique information. They're just giving you sort of redundant or not particularly vital information. Okay, how am I doing in time? Blown past, okay. I'll skip this entirely then. Okay, takeaways. So the key point in this project is just look at, we imagine this full space with all these possible interaction degrees, but in practice, we see that only a few of them, only the first 6 or 7 or 8 different ones are actually necessary to solve the problem. All the higher ones are there, they are being used somehow. If you cut them out and remove them, it's almost as good as having, the small number. Yeah.
Have you tried training multiple subsets and then combining them?
Like averaging them like an ensemble? No, I haven't tried that. Good idea.
That
Like
would be a
that.
dropout, right? Like
Yeah, something like that, right? Yeah, where you take each one like that. Good idea. None of them try that, but it's something that should do fairly well because each one is up individually. And then they add them together, you kind of cover each other's weaknesses, sort of. Yeah. Good idea. Yeah, so basically this gets to the idea of, this space is useful to the model. If it gets you beyond linear regression, but the sheer size of it is misleading because you're not really using most of it. Most of it is just sort of there in the background. Only thing you need to use is a small early portion of it. That's sort of the punchline of this. And that wasn't obvious going into this because, you could just assume that all regressors are being used in a good way because it's a machine learning model optimized to solve the problem. It'll find a way to use all of them usefully. The answer is no. Only finds, good answers for a small number of them. Okay, and that's, yeah. So, I mean, the final last takeaways, obviously these networks are doing something more powerful in regression. But in both the quantum case and the classical case, some of that, largest in complexity was not necessary. Either coherence could be removed, more ancilla undoes the damage basically, or, shrinking the space down to a small space is almost as good as a full space. So there's some, yeah. Go ahead.
Maybe I can ask again, but so the traditional wisdom around selecting which one of your parameters are relevant and which one are irrelevant is just putting a L1 regularizer at the end. Is this something you've tried, and does it inform your decision of which degrees to keep and which ones to throw away?
Yes, I never tried. I mean, usually L1 regression I've seen is on the parameters of the network itself, not on the elements of W that you create after contracting it. So I'm actually not sure. Yeah.
Why not?
I'm trying to think of how you would do that because there's a lot of them to incorporate. There's probably some way you could like treat W, construct W. Yeah, you probably could. I don't know. Yeah. Yeah, that is one way of doing it. I mean, I was curious if it's just like, I didn't want the model to, I wanted to sort of force the model to only use those outright, not at a penalty that, could bias towards one or the other. I want to just outright say, only is it there, how well does it do? But yes, you could use some smoother or softer penalty to it. Yeah. Yeah.
As of now, you're not using any penalty, right? Not L2.
No,
right?
no penalty.
Even L2, I think you would zero in on some of them. You wouldn't set them to 0, but you would still.
Yeah, I'm trying to think of a penalty on W itself. It should be not that hard to do. It should be, because the problem is really that you can't do that individually because there's too many parameters in W, but there should be a way to give rise to that penalty via, factorized sort of penalties to it. Yeah, it should be possible to do. Well, although no, because I don't want necessarily to share penalties across all degrees. I want to be able to set a given degrees penalty uniquely. Should not be trivial to do, actually. I don't know. Think about that. Anyway, yeah. But yeah, no, I'm not using any penalty in this case. No L2, L1 penalty. No questions other than that? Maybe. Let's cut it. Yeah. Thank you. Yeah.
So there's something, maybe you can just comment on something I'm thinking is a little odd, which is you kind of showed that without adding any features, your W can perfectly memorize any training set.
Right, if they're orthogonal or not, yeah, they don't overlap.
Right?
Yes.
Without adding any features. So it's already like, so that makes it super expressive. And so adding features,
We say adding features, right? Exactly that.
well, like you're adding, 1 X, like you're
Well, I'm saying if you have W, if you have that kind of iteration, actually like sine and cosine is probably a better one to use. That one, it's very easy to give rise to orthogonal states from that. Like, because you have, so many number of features are individually being interproducted together. If one of those is orthogonal, you get 0 overall, right? Yeah. So that means that it's very easy to create W, but it's taking the combination of your samples and just putting the label you want in the end out. The overlap of that is only going to give you one output. So it's just trivial to create a 0 loss W for that problem, right?
So let me ask something a little different.
Yeah.
Which is when you're taking these degrees.
Yeah.
And you're saying this is a way to truncate your function by throwing out some degrees. Is that like reducing the bond dimension of your like an NPS or something? Is there some clear connection between that and the bond dimension or the entanglement or something like
I think the answer is, unless you go really extreme, no. Even a relatively low degree one will still be using all the rank of the network. That's my, I think, belief about that. It's like, unless you go like linear regression, which is a very small rank required, if you go up to, triplets or beyond that, you already are going to be exceeding, a reasonable bond dimension of 20, let's say. You're already going to be saturating that complexity. Because there's just there's so many pairs and triplets you can create. All of those are arbitrarily set. You're just already going beyond the rank of the MPS. So unless, the truncation does not actually make, generally speaking, for a cheaper network, you still need to have all that bond dimension there to be able to even do a truncated portion of it.